Title of today's lecture is Pancreas and Small Intestine. So where we're going to start here is, and it seems like these things are unrelated, but I don't really just want to do a single lecture on the pancreas. This helps this, okay? And they're attached together and they're in roughly the same place. So let me give you some basics here. Pancreas. The pancreas is two organs in one. It has both endocrine and exocrine function, which is not entirely useful to you unless I tell you what each of those things mean or remind you if you already knew but forgot. Endocrine, I'm going to break this into two categories here. Do endocrine here, and I'll do exocrine over to the right here. We'll get to it. Endocrine. Endocrine. Anything endocrine has to do with hormones. Okay? So anytime you hear the word endocrine, I want you to think hormones in some way. Okay? Now, when people think hormones, they normally think about that as you get into your teens, your body will begin to change. Okay, yes, that is one set of hormones. Okay, there are a lot of others too. And the pancreas really doesn't deal with those types of hormones. Okay, the ones that it deals with have mostly to do with blood sugar. Now, hormones are basically, and I maybe give you a brief definition of that. So, hormones, I've talked about them before, are chemicals made by cells in one part of the body put into the bloodstream to signal or control other cells. And that's really the goal of hormones. Basically, we're sending it through the blood to tell some other cells what to do. Not necessarily to boss them around, but to help them be able to regulate or be a part of what the rest of the body is doing. In this case, the endocrine part, so that this is the reason it's called endocrine. Endo means inside of, or internal, or into, okay? And so because the things it secretes are going into the blood, which is part of the internal environment, therefore it's considered endocrine. So the hormones produced by the pancreas two main hormones, and I bet you probably know one of them. Give you a hint. Blood sugar.
Insulin.
Yes, insulin. Okay. Insulin. Now, insulin is a hormone that enables cells to absorb sugar, specifically glucose, which is known as blood sugar, glucose from the bloodstream. This is really important, and it's a regulation that happens a lot. And it's like a constant adjustment that happens, okay? Because you eat a meal, your small intestine will absorb the carbohydrates and sugars, and in your bloodstream, your blood sugar level is going to rise as a result. But your pancreas then responds shortly thereafter with the appropriate amount of insulin in the bloodstream to allow all the cells to absorb the appropriate amount of sugars out of the bloodstream. It's incredible, the system. But there are cases where this does not work correctly. What do we call that disease or group of diseases? Where people have issues with blood sugar. Diabetes, yes. So, two types of diabetes. Diabetes insipidus, diabetes mellitus, or type 1 and type 2 diabetes. And basically what it is, in type 1 diabetes, they're insulin dependent. Basically what happens is their body has, for whatever reason, waged war against their own pancreas and murdered all of the cells that produce insulin. That's what autoimmune disease is. Why does it pick on those cells? I have no idea, okay? But in some people it does. And therefore, they can no longer produce their own insulin. And they have to inject it or have a pod that secretes it, and dial in on their phone or on a pump to put it into their bloodstream, things like that. Well, then there's type 2. Type 2, you're producing all the insulin that you need, but your body is no longer responding to it as it should. This typically has to do with obesity. It's not to say that every person that's obese will develop type 2 diabetes, but it definitely increases the risk factor. It means that the cells no longer respond to the insulin in the way that they had done previously. So that's type 2. Okay. Now, the second thing, this insulin will lower blood sugar. And the way it lowers it is it allows the cells that are next to the bloodstream to absorb the sugars from the bloodstream, right? So now insulin can kill somebody. If somebody is injected with straight insulin in a large enough quantity, it would murder them, okay? Because basically it would tell the body, the cells, pull all the sugars out of the bloodstream. And that would, if that dropped to zero, people would pass out. I mean, and if it's bad enough, they would die. Okay, so this can be a really dangerous thing for injection if it's not regulated right. Okay, and hey, why does it have to be injected? Why can't we just, take a pill for insulin? Anybody know? See? Okay, well, I'll be devil's advocate for a second here. Like if I took Tylenol, it would go into my bloodstream eventually. Yeah, so one thing is going to be speed. We want it to get there fast. But the other issue is insulin is a protein. And the trouble with this, if we eat a protein, what happens to that protein? Yes. And if insulin gets broken down, it's no longer insulin. Okay? Has to be folded a very specific way to be able to do that job, so it has to be injected. Now, how we make it, because it's a protein, this is actually kind of, I don't know, no one's going to fight for their rights, I don't think, but we enslave an entire species of organism to create insulin for humans. But no one's out there picketing because it's bacteria. We give bacteria a plasmid of DNA that codes for insulin, and they just start cranking out insulin. They have no idea why. Then we isolate the insulin, put it in vials, and give it to people so we can go on without trouble like that, or as much trouble. Yeah. But no one's like, free the bacteria. Nobody cares about them because they're not fluffy and cute, All right. Well, then another one here is number two is glucagon. Here we go. Glucagon. I joked yesterday, that sounds like the name of a transformer. I am glucagon. I don't know. Okay, so glucagon is a hormone that allows glycogen to break down and put glucose into the bloodstream. And put glucose into the bloodstream. Let me talk briefly about glycogen here. Glycogen is a polysaccharide. Let me make sure I spell it right. I would feel bad. Yeah, it's 2 C's. Polysac. H-A-R-I-D-E. Polysaccharide. Which means that it's basically a chain of a bunch of glucose stuck together like that. And so glycogen glucagon goes in and breaks these bonds apart to make individual glucose molecules. So polysaccharide of glucose, and it is stored in the liver and muscles. Your muscles have a nice little glycogen store to help you push through when you need to have more energy, like let's say you're running a 400, okay? Or you're doing some kind of athletic activity and you need more glucose than what was freely available. Glucagon helps break that down. So this one will actually raise blood sugar. You're like, well, why is that good? Well, we need these two things together to help regulate and keep the blood sugar at a consistent level. If it drops down too low, glucagon will be released to raise it back up. If it gets too high, insulin gets released. Hey, you guys remember all the way back to Unit 1 when we talked about the feedback systems and homeostasis? It's negative feedback. Negative feedback. As blood sugar begins to raise, our body responds by putting in insulin. As the blood sugar begins to lower, glucagon goes in to bring that back down. So, okay, I should have drawn a pancreas here, and it's not gonna be great, but I'll put one up here. Pancreas. It's a little longer. It's a long and goes across, and basically it's like that shape right there. Okay. And if you want to do some cross hatching here, because it looks extremely glandular, and I know that's not helpful if you've never seen a gland before, but it looks like cottage cheese, but where the cottage cheese clumps are super, 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 super close together. Now, on a cellular level, if you were to zoom in on it, you would see there's little sections in here, so draw some like dots like this. If you looked under a microscope, these sections look different. The cells that are in these little clusters and sections, they look different. Now, from the outside of the pancreas, you can't tell, but these are called islets of Langerhans. Islets of Langerhans. They're also now known as just pancreatic islets. Islets is like a tiny island, okay? So most of the pancreas is exocrine function, but the hormones, so are all produced in the islets of Langerhans, these little sections that have these dots here like that. So I'm going to go back here. Hormones produced by the pancreas in islets of Langerhans. Depending on when you study this, you'll find there's a trend, and I think I've mentioned this before, where the names of the scientist is getting removed from stuff, and it's to give it more of an anatomical name or physiological name than just having a bunch of things named after scientists. So that's why they were later renamed pancreatic islets. But Langerhans was the scientist who discovered them to begin with. Okay, so if the insulin and glucagon are made pretty much just in those little dots there, so what's the rest of it for? The rest of it is for the exocrine function. exocrine. Exocrine means secretes onto a body surface. A body surface or the external environment. Okay? External environment. So, for example, like if you didn't wash your hair for a couple days and it looks greasy, it's because there is oil, like a waxy oil, produced on your scalp by what's called sebaceous glands, which produce something called sebum, which is that wax. And those are exocrine. In your ear canal, there are ceruminous glands that produce earwax, or cerumen. Those are exocrine. Your sweat glands producing sweat onto your body surface, also exocrine. Okay, mammary glands, excrete milk to the outside world. Okay, so that's also exocrine. So you're thinking, if this thing is deeply embedded into the body, how in the world is it going to be exocrine? It's not going to start dumping out stuff onto your skin. It's because the body is a donut. Okay? So this stuff makes pancreatic, forgive me for saying this, okay? This is the word, I didn't make it up. Juice. That's nasty. Like orange juice, grapefruit juice, pancreatic juice. Okay? Pancreatic juice is secreted into the first part of the small intestine, known as the what? Spot your letter. D. DJ Ice. All right. What was it? Yes, duodenum. I've heard it pronounced duodenum or duodenum. I don't know that either one of them is necessarily right or more right. Okay. All right. Because it is being secreted into the intestines, and the inside of the intestines is the external environment of the body, it's considered an exocrine gland as well as an endocrine gland. All right. And I'll just put that in parentheses. In the intestine is the external environment of the body. Okay. So we make between a liter and a liter and a half of pancreatic juice every day. It's just the same quantity as 1.0 to 1.5 liters of pancreatic juice per day. That's how much we're making. And what's in it? Contents of pancreatic juice. What would you think the number one ingredient is? What was the number one ingredient of saliva? It's simple. Water. Water makes up the majority of it. Okay? And these are like, think about it. We got to make a liter to a liter and a half of saliva a day. We got to make a liter and a half of pancreatic juice to begin to understand why water is important. I mean, it gets recycled in a lot of ways within the body, but we have to replenish it. Okay? Water, and it produces a lot of digestive enzymes to help break stuff down. But something else that's really crucial, that is highly underrated, and it's this: ions. Okay? Primarily bicarbonate. And bicarbonate is HCO3 minus. Okay. This raises the pH. Because coming from the stomach, we have chyme. Chyme from the stomach has a pH between 1 and 2. That's extremely acidic. But by the time it turns into poop, or feces, I just wondered if you're being facetious, does that mean you're being a turd? Okay. All right. So, by the time it turns into poop, the pH is 8. Poop is alkaline. It's actually shifted all the way from an acid to the base side of the scale, and it has everything to do with this bicarbonate ion that's produced here. Otherwise, your small intestine would be torn up by all the acid in there. Your stomach encounters acid all the time, but the stomach's set up for it. It's got that mucus gel layer to protect it from eating itself. Okay, the small intestine has no such protection. It has some mucus, but nowhere near this. And I remember for this from the lecture earlier, the mucus gel layer that exists in the stomach, there is no such layer in the small intestine or large intestine. So we have to quickly shift that pH back to this range. In fact, by the time it gets to the large intestine, it's already at 8. In fact, bacteria that live there have to be able to live in an alkaline environment. So much so that some of the primary residents in the large intestine is a bacteria. The bacteria's name is Alkaligenus faecalis. And its genus and species, alkaligenous because it lives in an alkaline environment, faecalis because of what? Faecalis. Any guesses? Feces. You're like, why do you keep going back to feces? Because, it's important. We got to poop. All right. Now, small intestine. I'm going to try to fit this all into a small area, which is how the small intestine feels anyway. Trying to be packed into a small area. So I'll maybe draw a little line here. Okay. Small intestine. There are 3 sections. 3 sections. You know the first one now. What's it called? The duodenum. Duodenum is the first 10 inches, give or take. So it's not very big. It's considered to be the mixing tank of the small intestine. As it receives. And when I say chyme, that's your digested food. That's what it's called once it leaves the stomach. It's like basically a soupy, highly acidic soupy mixture. So chyme from the stomach. Juice from the pancreas. And bile from the gallbladder. And mixes all that together. So it's just the first 10 inches. In us, like if you're looking in your cat, it's probably about the length of your thumb or maybe just a little bit longer than that. It's not huge, okay? Because cats don't have 23 feet of intestine. I don't think they come even close. But we do, yeah. Maybe about 23 feet-ish. Okay, it's not exactly going to be 23 feet for everybody. That's just a ballpark figure there. Okay. 2 is jejunum. Jejunum. That's about 8.2 feet in most people. That's where most nutrient absorption takes place. And it's not the longest section, but the anatomy, the fine anatomy of how it's set up means that most nutrients will be absorbed here. But the small intestine, I don't want to say, yeah, maybe I will, arguably is the most important part of your entire digestive tract, because that's where the absorption actually takes place. Unless the nutrients are absorbed, your whole digestive tract is useless. There's no point of it. You don't eat just to make poop. You eat to get the nutrients out, and you poop out what's left. Okay. Finally, number 3 is the ileum. And that is about 11.5 feet, give or take. And make sure to spell it I-L-E-U-M, not I-L-I. If you do I-L-I-U-M, that's the name of the bone in the pelvis, I-L-E-U-M. So this is the longest section. Of small intestine. And it connects with the large intestine. Okay. Now I'm going to do a cross section, and I'm going to look at one little part here as well. Okay. Now, the anatomy is slightly different in each of these sections, but they'll all have this. Okay. So, draw a circle. Say cross section of small intestine. Okay, we're going to draw a circle within the circle because there's tons of layers here, and I'm going to draw another circle within that circle, and there would be a bunch more, but just a few for right now. Outside is serosa. Then you have a number of layers of smooth muscle that help move things through. But then I want you to draw some hills in there. They don't have to be very even looking, but they're big hills that kind of push in. The walls of this sort of push in to make these hills. These hills are called, or hills are folds in the intestines. They're called plica. These are folds. And the folds are there to increase the surface area inside the small intestine. Then I want you to cover everything with shag carpet, because everything is covered with shag carpet. There are all these extensions. In the small intestine. And these extensions, the shag carpet, are called villi. Okay? It's the carpet. And it makes sense, guys. It makes sense. I've got one to show you here. I thought I did. This pattern repeats itself. It's not ideal because it's right. This pattern repeats itself in things that do a good job of absorbing. Here's a washcloth. And if you look at the surface of the that's gross, sorry. I've got some dishes I gotta wash. Okay. Yeah, but you see all of those little loops and extensions. That's what makes a washcloth or a towel so absorbent in comparison to our school paper towels. Okay? Is they increase the surface area. So here is what a villus looks like if you were to zoom in on it. I want you to draw this spike like this. Okay? And I want you to draw a spike within the spike. All right, so this is a single villus. which is a singular of the villi there. That spike within the spike there is part of the lymphatic system. This is called a lacteal. The reason it has that name is because it's kind of milky or opaque. Lacteal absorbs fats or lipid-based molecules because we can't put them directly into the bloodstream because oil and water don't mix. But we do have in here, coiling around this lacteal, what do you think this is that I drew, and why did I switch colors? That's right, a capillary. And that capillary is going to absorb most of the nutrients. Absorbs nutrients. So you got all these nutrients, guys, because in the small intestine, there's no solids. It's all liquid. Okay? Everything's broken down. But all this nutrients in this liquid are gonna travel through, and this outer edge right here is just a single layer of cells. So just a real thin layer, a single layer of cells, epithelial cells that are just allowing things to be absorbed pretty much straight through. And they're floating through, and if it's lipid based, it's going to get picked up by the lacteal. The lacteal is part of the lymphatic system. So it's going to travel to lymph vessels to be processed in order to be able to be absorbed eventually, but it can't go right into the bloodstream. So that's going to absorb the lymphatic stuff, and it will eventually dump into the bloodstream once it's processed. Okay, so every one of these right here is one little fiber in the shag carpet, and you have all of those. And then you have these folds in there as well. Okay, so surface area is the name of the game. Let me steal a little spot right here. You can write this in wherever you can fit it. Because of villi and plica, the absorptive surface area goes from 3.6 square feet to 2,200 square feet. All right. If you look on the floor next to you, the desks, if they're set up correctly, the desks should be about 2 feet apart. So you should be able to see 4 squares on the floor. If the intestines in your body were like PVC pipe on the inside, just completely smooth, little less than 4 squares would be all the surface area that you have to absorb your food. Okay? But because of villi and plica in the small intestine, imagine every desk and table removed from this room. It would be all the floor space in this classroom, plus my lab prep area, plus about a third of Dr. Powell's room next door. That's how much area you have for absorbing nutrients in your intestines as a result of this shag carpet and these little folds. So it's incredible. All right, and I think that'll about do it for today.